So in this tutorial we're going to look at the normal distribution, which is something that is normal and that is natural. It applies to all random situations really, and you'll see the normal distribution all over statistics, but it's not intuitive to us. It's rather surprising. So to understand the normal distribution, it's a good idea to start with an example. So let's use this example. Let's imagine what's called a Galton board or a bean machine, where at the top we've got a cup filled with balls, and we're going to, at some controlled point, allow these balls to go through one by one. And they drop into some bins at the bottom here, so they can drop into either bin A, B, C, D, E or F. And we're going to make them go through some rows of pins. In fact, we're going to draw 5 rows. Each time they go through the pins, they have to either go left or right. So there are 5 times when the ball is going to have to choose, in a sense, whether to go left or right. But of course, it's a completely random situation. So whether it goes left or right is left up to chance. Well, what's going to happen? You might think that the balls will evenly spread themselves between all 6 bins. So we'll get 5 or 6 in each bin. What actually happens is rather more interesting, and this is what we mean by the normal distribution. The normal distribution isn't a flat shape like that. In fact, it's a particular curve. So let's have a look at that. Let's zoom in to those bins and consider just one ball. Now that ball can go either left and then left again, maybe, and then left again in this row, left and left. So it might go left 5 times, in which case it will end up in this bin here. If it goes left though, let's say 4 times, and then goes right, you can see it'll be left, 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 and then right. It ends up above this bin here, so it should appear in bin B. Okay. Now it turns out that although there's one way it can go into bin A, there are 5 ways it can go into bin B. Why is that? Well, it's because if we think of the ball going left, 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 and then right, we might also think, well, it could go right straight away. So it goes right and then left, 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 left. Or it might go left, left, right, left, left. And how many ways are there for it to get to exactly the same position? Well, in fact, we call this the combinations function, or the choose function. There are 5 choose 1. And 5 choose 1, if you use the button on your calculator, will give you the answer 5. So if I run the animation, what we should expect is that because there are very few ways of the ball getting in this bin here, then not many balls, maybe just 1 ball or no balls will get into this bin here. But similar on this outside bin here, because it would have to go right, 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 right to get into this bin. That's not going to happen very often. There are no other ways of it getting into this bin. Whereas we'd expect a lot more, in fact 5 possible ways of getting into this bin, just as there are into this bin. And here there are in fact 10 ways of getting into this bin. So when we run the animation, you'll see that happening. At first it seems very random, but then a pattern emerges. Since there are more ways for the balls to get into these 2 central bins than there are these 2 bins, B and E, in fact twice as many ways, we get more balls and in fact what we call a central tendency. Then as we go out from the center, which we can call the mean, it's the average if you like, the mean average. So we go out from the center, we get fewer balls until we get to the bottom here, to the edges here, where it's hardly likely at all that we're going to get any balls into these bins, because there aren't many ways of getting into these bins. Okay, now we can quantify that, and we'll do that in a moment. But the first thing that we should have a look at here is simply what is the shape that we've ended up with here. We might have been expecting a very even shape since we knew it was random, and we thought, well, maybe they'll evenly go into each bin. In fact, though, what we've got is a curve. The curve has a very obvious symmetry to the left and right of the central tendency. Also, it has a rounding off at the top and a rounding off at the bottom here. Otherwise, this is pretty much a diagonal, and we end up with a shape shaped like a bell that, in fact, we usually refer to as a bell curve, the bell curve of the normal distribution. So this piling up effect is perfectly normal, and it's what we would expect. The evenness, in fact, is rather unusual, and that would indicate that we didn't have a random event. All right, let's have a look at a second problem, and this time what we're going to do is graph the frequency of the outcomes. So what we'll look at this time is, let's say, flipping a coin. So we'll have 10 flips. Let's call it just 10 coin flips. So 10 flips of the coin. So 10 coin flips. And this time what we'll do is draw a graph. So the graph will be very similar to the Galton machine or the bean machine that we were looking at in the first example. But this time what we're going to do is actually calculate the frequency. So on the vertical axis here, let's label this frequency. And in fact, because I know that with 10 coin flips, if we're looking at the number of heads, that frequency is going to get quite high. So let's have a look at, well, let's say, what about if we number up in 20, so 20, 40, 60, 80, 100. So we'll say this is 100. There are 100 ways, or 20, 30, 40, 60, 80, 200, and so we'll finish our numbering at 260. Okay, so 10 coin flips, and we're looking at the number of heads. So how many ways are there of getting no heads whatsoever? In other words, all tails. Well, again, if we think of our combinations formula, this time let's write it down. So we'll be talking about 10 events. Whoops, let's make that a bit clearer. So 10 events, out of which we get no heads. So 10, we say choose 0. 10 choose 0, you can use your calculator, or you can use the formula. If we use the formula, 10 factorial over 0 factorial times 10 factorial is going to give us, 10 factorial just means 10 times 9 times 8 times 7 and so on, right down to 1. So 10 factorial divided by 10 factorial is going to just give us 1. And you need to know that 0 factorial equals 1. So we've got 1 divided by 1 times 1. In other words, 10 choose 0 equals 1. So we're expecting only to get 1. In fact, there's only one way, we could say, of getting 0 heads. In other words, all tails. Now, similarly, if we think of getting all heads, so that would be 10, choose 10 ways, we would have a very similar formula here, but this time 10 factorial times 0 factorial in the denominator. But you can see this is simply swapped around the other way, which doesn't make any difference, so the answer again will be 1. And so already we can see, if this is 10, our central tendency. We're going to have very small numbers at the edge of our normal distribution, and in the middle here we're going to expect a very high frequency. Okay, let's think of then the chances of getting just one head. In fact, let's number this up straight away. Okay, so our central tendency is going to be around 5. And now we're thinking about the frequency of getting one head. So how many ways are there, in other words, of just getting one head? So we have 10, choose 1. Well, that's 10 factorial over 1 factorial times 9 factorial, n minus r. And 10 factorial is 10 times 9 factorial, so then the 9 factorials will cancel, leaving us with 10 divided by 1 equals 10. So there are 10 ways of getting one head. So that would be here. And it must be the same for 10 choose 9 also equals 10. So if we get 9 heads, that would also be, there are 10 ways of doing that. So if we continue with this, we'd now have 10 choose 2. Well, that's going to be 10 factorial over 2 factorial times 8 factorial, which is going to be 10 times 9 times 8 factorial, so that cancels, divided by 2, which is 5. We do a little bit of cancelling to make the maths easier, to make the arithmetic easier. 5, 1 gives us 5 times 9, 45. So there are 45 ways, in fact, of getting just 2 heads. So let's have a look. Where's 45? Well, it goes up in 20s, so this must be 40, so that would be 50, so that would be about here. And similarly for 8 heads. So there are 45 ways of getting either 2 heads or 8 heads. What about 3 heads? Well, now the numbers are going to get more interesting. So we've got 3 factorial over 7 factorial. That's going to be 10 times 9 times 8 times 7 factorial divided by 7 factorial, so there's where it cancels. And now we've got 3 factorial, which is 3 times 2. So here we can cancel the 3's. 1 and 9 divided by 3 is 3. And maybe leave the 10 but cancel with the 8. So now we've got 3 times 4, which is 12, times 10, which is 120. So, number of ways of getting 3 heads. We've now got 120, which is there, and that must be the same for getting 7 heads. What about 4 heads? And of course 6 heads. So now we've got 10 factorial divided by 4 factorial, and then 10 minus 4, so 6 factorial. So we've got 10 times, now we need to be a bit clever here, 10 times 9 times 8 times 7 times 6 factorial, so that cancels the 6 factorial, divided by the 4 factorial. So that's 4 times 3 times 2 times 1, and we don't need to write times 1. Now, how are we going to cancel this out? Again, the 3's and the 9's very easily cancel. The 4 with the 8 seems an obvious way to go, so that'd be 1 and 2 there, and then we can just cancel those 2's. Okay, what are we left with? 10 times 3 times 7. So 3 times 7 is 21. 21 times 10 is 210. So it really has shot up here, so that 4 heads, we need to now record this up here as 210. And similarly for 6, 210. Now that just leaves us with our central tendency, which is 10 choose 5. And here we've now got 5 factorial times 5 factorial in the denominator. So we've got 10 times 9 times 8 times 7 times 6 divided by 5 factorial, so that gets rid of one of the 5 factorials. Let's just write that a bit neater. So now we've got 5 times 4 times 3 times 2. Okay, well 3 times 2 and 6 cancels immediately. Let's think, what are we going to do now? Let's cancel that, so we've just got 1s here. Let's cancel the 4, so we've now got 2 here, and divided by 4, 2. Whoops, we've got 1 there, sorry. Okay. So that's now just left 5 in the denominator here, so we're going to cancel with the 10, so that's 2. It's a little tricky to see, but we've got 2 times 9, I'll write that out a bit neater, 2 times 9 times 2 times 7. Okay, what's the easiest way to do that? Well, 7 times 9 is 63, so we've got 4 times 63. So 2 times 63 would be 126, so we've got 252. Okay, so our central tendency is 252, which, well, if it's 240 here, it's 250 there, it's going to be slightly above, so let's say it's there. And now we can see very clearly, more clearly than the previous example, I think, the central tendency of the, not just the central tendency, but the bell curve shape of the normal distribution. And the reason why this is such an important shape is that we'll also find this in other situations when we're taking statistical information, when we're gathering data. If we gather data and we see this bell curve shape, then we'll know we've got a normal distribution, so the sort of thing that's produced by random forces. All right, finally then, let's join up our crosses here, our plots, and see the bell curve shape. So very carefully, let's just join them up. And there we've got a more accurate picture of the bell curve shape. Okay, finally, what's this got to do with statistics? Well, let's have a look at the same bell curve shape cropping up in a set of data that I've collected to do with the weight of cats. So let's draw a grid. I've recorded the weight of 100 cats. So we've got a 10 by 10 grid. And the data that we're going to fill in is going to be rounded. So to make life simpler, I've just rounded to the nearest pound. So let's have a look at that. So it's nicely ordered. We've got 2 4s, 2 5s, 2 6s, 5 7s. We've got how many? 10 plus these 9 here. We've got 9. Oh no, we've got a lot of 8s. We've got an awful lot of 9s. A lot of 10s. Now it tails off again here. So 11s, we've got 4 11s, 2 12s, 2 13s, just 1 15, 1 16, 1 17, and a big fat cat that seems to have come in at 19. Now something to be aware of here is that of course these aren't exact values, these are rounded values. So this could be as low as 3.5 because we'd have still rounded up to 4. And this could be as high as 19.5. 0.49 recurring, so just under 19.5. So these, in fact, are categories, and that gives us an important concept, actually, which is worth just jotting down here. It's important to remember whether you've got discrete data or continuous. Now, discrete data is the sort of data that we've been looking at with the coin flips and with dice examples and so on, where there's just one number that it could possibly be, and there's no gradation, if you like, between the 4 and the 5. But in this case, of course, the weight can be any value between 4 and 5. It can be bang on 4, it can be bang on 5, but it could be any value. So we call this continuous data. So weight and height and those kind of things are good examples of continuous. Excuse me, let's just spell it correctly. Continuous data. So important to identify that first. So it's not discrete data that we're dealing with here. So let's cross that out. It's continuous. Okay, now that will help us when we draw our graph. And let's draw our graph now. So again, if I give ourselves a pair of axes here, if we number up our axes then using the idea of continuous data, we'll need to go right up to, well, if we go up to 18.5, so let's just draw these marks in here first. If we go up to 18.5, then over 18.5 will give us this 19 here. And what would this need to be? Well, it's the boundary between 4 and 5. So in other words, this is going to be 4.5. So not 4, but 4.5. And the next boundary is going to be 5.5. So let's just squash it in like that. 5.5, 6.5. In fact, these are always going to be odd, even numbers rather. 8.5, so then 10.5, 12.5. And just make sure you number up your axes accurately. So here we've got our 18.5. Okay, so let's put these in. 7.5 rather is this boundary here. 7.5, 9.5, and so on. Okay. So, what is this? These are the intervals of weight. So we are recording here the weight of the cats in pounds. So old-fashioned measurement, LB is the symbol for that, in pounds. Okay, that's done the horizontal axis then, divided this idea of weight into intervals so we can record the value in each interval. And now, for the vertical axis, well, if you look at the most frequent, the modal number, then you'll get what we call the modal category. So let's record that. So what's the mode? Mode is 9, so that's the most frequent number. And if we look at the most frequent number 9 and how many there are, we've got 10, 20, we've got 20, 30 up to here, so we've got 33. So we need to take our numbering up to, I'll just make a little note, we've got 33 nines. So our vertical axis needs to go up at least to 33. So let's divide it into 7 equal parts then. There we go. And number up in 5. So we've got 5. Up to 35. And this axis is recording frequency of weights. Okay, so let's label our axes. Now we've got to do is transfer the data onto the graph. So first of all, what about the first interval here, this category here? There are 2 4s, so if we record that mid-interval, and some people would want to draw a bar here. If you were going to draw a bar, then you would have to make sure that the bars join up. So unlike a bar chart, you would make sure these join up because this is continuous data, so you wouldn't have a gap. It's perfectly fine though just to do a cross at the top of your bar if you like. And let's now look at the second interval. So between 4.5 and 5.5 there are again two cuts. We're at that weight. Between 5.5 and 6.5 there are once again 2. Between 6.5 and 7.5 cats now there's a bit of a leap, so we've got 2, 4, 5, so we can go up to here. Is that about right? Yeah. And now in this interval here between 7.5 and 8.5, so 7.5 and 8.5 is going to be these 8s here. How many have we got? Well, we've got 20 up to here plus 2, 22. So in this interval here, up to 22. You can draw a straight line, but I think it's okay just to look very carefully. There we go. It's about there. It's going to give us a good enough plot. Now, we deal with our 9s, so that's in the 8.5 to 9.5 category. That's our highest value, and we've already said we've got 33, so up to about here, 33. Is that about right? Maybe a little up there. Okay. Okay, I'm just going to redraw that. It's important we get it as close as possible. So I just want to get it right in the center. There we go, something like that. Now, we're going to expect to come down here. So we've done the 9s. How many 10s have we got? We've got 10, up to here would be 20, plus another 2. So it's 22 again. So nice and neatly, let's get it in the right category. 22 is going to be between 9.5 and 10.5 then. So here. Okay, that's about right. And then how many 11s have we got? So in the 10.5 to 11.5 category, we've got 4. 10.5 to 11.5, 4. So that's going to be about here. Okay, and we've got 2 12s. So that's going to be here. We've got 2 13s here. 1 15, so now wait a minute, we're missing a 14, so there were no 14s. Okay, so we need to record that at 0. So that will be down here. Now we've got 1 15 in this category, 1 16, 1 17, no 18s, and 1 poor cat that's in the 19 category, so that will be about there. So finally, let's get a different colour and draw up our graph. So very carefully have a look at what we've got. Okay, so it's not exactly as predicted, but you can see very clearly again the bell curve shape.